Chapter 4.4 is going to be exponential equations and logarithmic equations. So we'll start off with exponential equations, and we'll see that there's essentially two different ways that we can be, that we'll try to solve exponential equations. So exponential equations are just going to be equations that have variables in the exponent. So the first way that we're going to try to solve these is by expressing each side of the equation with the same base. If both sides of the equation contain exponential expressions that have that same base, or which we'll see in a couple minutes, or if we can rewrite them so that they do have the same base, once they have the same base, all we have to do is equate their exponents and solve for the variable. This method is called the one-to-one property. Okay, so for example, let's solve this equation here. We have 3 to the 2x minus 8 equals 3 to the x. So we want to figure out what x value makes this equation true. And then first thing that we should realize here is that these are exponential expressions on both sides with the same base. So since they have the same base, all we have to do is set their exponents equal to each other. The bases essentially cancel each other off. What we're technically doing is log base 3ing both sides, and it'll cancel that base. So we set the exponents equal to each other, and now we have a nice linear equation. We solve this for x, subtract x on both sides, add 8. I'm going to skip writing it because hopefully we're comfortable with that at this point. And we get x equals 8. So for checking this, we don't have to check these, but we'll see when we do the logarithmic ones that we actually have to check them. So I'm going to plug in an 8 to make sure it works. I'll put a question mark. Does that equal 3 to the 8th? So 3 to the 2 times 8, that's 3 to the 16 minus 8. So on the left-hand side, we do end up getting 3 to the 8th. So 3 to the 8th equals 3 to the 8th, so we know that we did the question right. So graphically speaking, we can think of that equation, both sides as functions. We can think of the left-hand side as y equals 3 to the 2x minus 8, and the right-hand side as y equals 3 to the x. But then we can graph them. So I'm going to go by intervals of 2 here. I'm going to let this be, I'll say 2, 4, 6, 8. So that's going to be 8 right there. And let's say that's the function y equals 3 to the x. So this is not to scale, this graph. So then we can graph the other one. And it might look something like this. So for the answer that we got an answer of 8, right, for this question. That represents the point of intersection if we looked at the graph for them. So once again, that's not drawn to scale, but that's similar to what it would look like, just so you have a graphical explanation for it. Okay, for the next one, we have 5 to the x equals 125. So these are not the same bases, but we can rewrite them with the same bases. So we can rewrite 125 as base 5, which would be 5 cubed, because 5 cubed equals 125. Once we have those same bases, we equate the exponents, and we get x equals 3. Which we go back to the problem, and we're like, okay, yeah, that makes sense. 5 to the 3rd does equal 125. Okay, so next one, 2 to the 3x minus 8 equals 16. So once again, we do not have the same bases here, but we can rewrite with the same bases so that they have the same bases, so we can just equate the exponents. So we can't do anything to 2, but we can rewrite 16 so that it is base 2. We can rewrite 16 as 2 to the 4th. So now that they have the same bases, we can equate the exponents. We have a nice little linear equation. We add 8 on both sides. We get 3x equals 12. Divide both sides by 3. We get x equals 4. Next one, we have 27x to the x plus 3 equals 9 to the x minus 1. So both of these, we're going to have to rewrite both of those. So we can rewrite both of these with base 3. 3 cubed equals 27. And 3 squared equals 9. So make sure you have parentheses. Now we still need to simplify this a little bit. So we have to remember that power to a power, we multiply the exponents. So it's going to be 3 times the x plus 3. And then 2 times the x minus 1. And in this step, I'm just going to distribute the 3 to get 3x plus 9. I'll distribute the 2 to get 2x minus 2. And now let's drop the base. We have common bases. We can equate the exponents. We get 3x plus 9 equals 2x minus 2. So I'm going to subtract 2x on both sides and subtract 9 on both sides. And I'll get x equals negative 11. Okay, and then just keep in mind you could check all of these if you wanted to by plugging them back in the original. Okay, so let's do maybe like three more here just to see all possible types we can see. So we have 3 to the 1 minus x equals 1 over 27. So we have to pull a little bit of a trick here. We have a fraction 1 over 27. We have to rewrite this as 27 to the negative 1. Right? 27 to the negative 1 is the same as 1 over 27 to the positive 1. Once we do that, it probably becomes more clear what we're going to do. We're going to rewrite 27, so it's 3 cubed, just to get the same base as 3. And then this is going to be 3 to the negative 3, so power to a power, we multiply the 3 times the negative 1. Once we have the same bases, we combine them. Once we have the same bases, we drop the base and equate the exponents. So 1 minus x equals negative 3. So I'm going to add 3 to both sides, add x to both sides, get x equals 4. Okay, and then for the next ones, let's do 2 more. So we have e to the x plus 1 equals 1 over e. So we have to do the same thing that we just did. It's e to the x plus 1 equals e to the negative 1. We have to rewrite it with the correct base. Once we get the same base, equate the exponents, and the linear equation is what remains. Subtract 1 on both sides, we get x equals negative 2. And one more. E to the x plus 4 equals 1 over e to the 2x. So same thing that we just did. We have to pull a little trick and rewrite this as e to the negative 2x. We get common bases, equate those exponents. Hopefully it's looking pretty repetitive at this point. I'll add 2x to both sides and get 3x on the left, subtract 4, 3x equals negative 4. Divide both sides by 3. We get x equals negative 4/3. Okay, so that's the one way that we can solve exponential equations. But obviously we will not always be able to get common bases on both sides. So for example, if we had something like 4 to the x equals 15, we could not rewrite those getting common bases, so this method wouldn't work. Or something like 3 to the x plus 1 equals 22 to the 4x. We could not get common bases here, so that method would not work. So if we cannot get common bases, what we have to do is actually use logarithms. So for this method, what we're going to do is we're going to isolate the exponential first. So we'll have some sort of exponential. We're going to isolate it. We're going to take the log of both sides. I'm always going to use the natural log. For all these examples, I'm going to use the natural log. So I'm going to take the ln of both sides. I'm going to simplify it using the power rule. So hopefully you remember that. And then I'm going to solve for the variable. So let's do that first one, 4 to the x equals 15. So it's good to have a kind of an idea here of what your answer should be. 4 squared equals 16. So our answer should be a little bit less than 2. So first step would be isolate the exponential. It's already isolated. It's just 4 to the x on one side. So the next step is going to be take the ln of both sides. So I'm going to take the ln of 4 to the x equals the ln of 15. Next step, we're going to use the power rule. So remember, for the power rule, we're going to bring down that exponent that's inside the input for the log. So it's going to be x times the ln of 4 equals ln of 15. And now you can probably see how it got split up nicely. Now the variable's not in the exponent. That's the whole point of doing this with the power rule. The variable is no longer going to be in the exponent. Now all we have to do is divide both sides by the ln of 4. So it's going to be x equals the ln of 15 divided by the ln of 4. And just always keep in mind that these are just numbers. ln of 15 is just a number. ln of 4 is just a number. So we can plug these in our calculator. And we're going to get, it's about 1.95, which makes sense. Okay, next one, we have 10 to the x equals 8,000. So I'm going to take the ln of, so the exponential is already isolated. I'm going to take the ln of both sides. ln of 10 to the x equals the ln of 8,000. And then the power rule, so bring down the x. X times the ln of 10 equals ln of 8,000. Divide both sides by the ln of 10. So x equals the ln of 8,000 divided by the ln of 10. And hopefully you are not thinking about canceling a 0 and making it the ln of 800 divided by the ln of 10. I would just plug it in your calculator exactly like you see right there. And we would get x equals about 3.9. Okay, so once again, should make sense because 10 to the 4th power equals 10,000, so it has to be a little bit less than 4. Okay, so let's do several more of these. 5e to the x equals 23. So first step, we have to isolate that exponential, which means we have to divide both sides by 5. So e to the x equals 23 over 5. And now we have to take the ln of both sides. So taking the ln of both sides, we get ln of e to the x equals the ln of 23 over 5. So the ln of e to the x, the ln and e inverses, they cancel. We're just left with x on that side. We're left with x equals the ln of 23 over 5. So make sure that you are not writing this as ln of 23 divided by the ln of 5. That is something different. So typing this in the calculator, ln of 23 divided by 5, we get about 1.53. Okay, next one, we have 40e to the 0.6x minus 3 equals 237. So we have to isolate the exponential here, which is e to the 0.6x. So we have to add 3 to both sides. So we get this. And then we have to divide both sides by 40, which gives us e to the 0.6x equals 6. Once we have that, same thing that we've been doing, we're going to take the ln of both sides. ln of e to the 0.6x equals the ln of 6. So ln of e raised to something, the ln and the e cancel. We're left with 0.6x equals the ln of 6. We're going to divide both sides by 0.6 and get ln, or x equals ln of 6 divided by 0.6. Plugging this in the calculator, it gives us x is about 2.99. Okay, and we'll do maybe 3 more. So 7 to the x plus 2 equals 410. So this one probably doesn't look too difficult. You probably know to start the same way. Take the ln of both sides. the issue here is when we do the power rule, we're bringing down the whole x plus 2 up there. Make sure you have parentheses around it. So that's why I put that one in here. Next, we're going to divide both sides by the ln of 7. So it's going to be x plus 2 equals the ln of 410 divided by the ln of 7. And then we have to subtract 2 on both sides. So it's going to be x equals the ln of 410 divided by the ln of 7 minus 2. So plug that in the calculator, we get about 1.09. Okay, next one gets a little bit harder here. It's going to look a lot different than what we've done. So we have 5 to the x minus 2 equals 4 to the 2x plus 3. So you can probably recognize that we have exponentials on both sides this time. So they're both isolated. There's nothing attached to them, so we can actually do the same method. Let's take the ln of both sides and then apply the power rule. So bring down the exponents. And we get this, making sure we have parentheses around them. So once you get here, you're probably thinking, what the heck do you go from here? Just always keep in mind that ln of 5 and ln of 4, those are just numbers. So this is just a linear equation. So we're going to try to get all of the x's on one side and all of the constants on the other side. So let's distribute the ln's. So it's going to be x times the ln of 5 minus 2 ln of 5 equals 2x ln of 4 plus 3 ln of 4. So you might notice that I put the variables in front of the, like I put the ln's last. That's just so you don't have to put parentheses around things to make sure you're not connecting them. Okay, so let's get all of the x's on one side. So I'm going to subtract 2x ln of 4, and I'm also going to add 2 ln of 5 on both sides. So I'm going to get x ln of 5 minus 2x ln of 4 equals 3 ln of 4 plus 2 ln 5. So I just got all the constants on one side, variables on the other side. We have all the variables on the left right now. So what we can do here is we can actually factor out an x. We'll be left with ln of 5 minus 2 ln of 4. That's kind of the tricky part there to recognize to do that. But hopefully you see what to do now. We have to divide both sides by ln of 5 minus 2 ln of 4. So we get this whole entire right side divided by ln 5 minus 2 ln 4. Okay, so we didn't approximate this whole time. That's the exact answer. Plugging it in the calculator and rounding just so we get an idea of what it is. It's negative 6.34 approximately. Okay, so let's do one more of the exponential equations, and this one's actually, excuse me, going to be pretty different from the other ones. So e to the 2x minus 4e to the x plus 3 equals 0. So taking a look at this and maybe trying to go by the rules that we had from the previous examples, we would try to isolate the exponential function, or exponential expression rather. We cannot isolate these exponential expressions. We have to recognize that this is in quadratic form. This is not a quadratic, obviously. It's not ax squared plus bx plus c equals 0, but it is in quadratic form, meaning it's something squared plus or minus that something plus or minus a number, essentially. If we rewrite this as e to the x squared, this might help you recognize it. So instead of having an x, we essentially just have an e to the x. So what I'm going to do here is we want to factor this, right? Every time we have a quadratic set equal to 0 like this in general form, ideally you want to be able to factor it. So it's going to be a little bit difficult to factor here, but if you set it up first, instead of having x plus or minus something times x plus or minus something, it's going to be e to the x plus or minus something times e to the x plus or minus something, because it's e to the x instead of x. So now we just have to think what numbers multiply to 3 that add to -4. That's going to be -3 and -1. So that was pretty easy once you kind of recognize it's in that form, because all we have to do now is use that zero product property and say if that times that equals 0, one of those has to be 0. So solving the one on the left, e to the x minus 3 equals 0. We add 3 to both sides, so now it's like we have these mini exponential equations. So we get e to the x equals 3. We take the ln of both sides, and we get ln of e to the x equals ln of 3. The ln and the e cancel. We get x equals ln of 3. And as a decimal, if that's how you want it as a decimal, it would be about, plug it in the calculator, it'd be about 1.1. Okay, on the right-hand side, we have e to the x minus 1 equals 0. So we add 1 to both sides and get e to the x equals 1. So take the ln of both sides, ln of e to the x equals ln of 1. We get x equals the ln of 1. Hopefully we don't have to plug that in the calculator. The ln of 1 equals 0. So we get these two answers. X is about 1.1 and then x is 0. Technically the answer looks better. Instead of rounding all these answers as 1.1, it technically does look better as the ln of 3 because that's the legit answer. But just so we have an idea of what it is approximately, I'm evaluating them. Okay, so those are exponential equations. As soon as we have a variable in the exponent, we know we're either going to have to try to get the same base on both sides and then equate the exponents. If we can't get the same base, we have to use logs and the power rule. So next, for logarithmic equations. So logarithmic equations are going to be equations that have the variable in the logarithmic expression, meaning it's in the input for the log. So for some examples of these, something like log base 4 of x plus 3 equals 2. And something else like ln of x plus 2 minus ln of 4x plus 3 equals ln of 1 over x. So you can see for that first one for A, we've actually solved those already. We would just have to convert that to exponential form and solve for x. For B, it's a lot more complicated. We have to use the rules, the properties of logs, and condense that in order to solve it. Okay, so starting off, we'll start off easier. So solving logarithmic equations using the definition of a logarithm. All that means is we're going to be converting these to exponential form and solving them. So the first step is to express the equation in the form log base b of m equals c. Essentially that just means isolate the logarithm. And then we're going to convert it to exponential form, solve for the variable, and we have to check the solutions. So we didn't have to check them for exponential. We just did it I did it once to just show us that we can do it. We have to do it for logs. The reason is we would have to omit values that make this original m, the original input, less than or equal to 0. So that's something to keep in mind. Okay, so let's do some examples. So log base 3 of x equals 4. So isolate the logarithm. It's already isolated. So let's just convert this right into exponential form. So exponential form is going to be 3 to the 4th equals x. 3 to the 4th is 81, so we get x equals 81. So we have to check our answer here. That one is pretty easy though, but we have to check. So it's going to be, we need to make sure the input, which is x, is positive in this case. So x is our only input here. We have to make sure that that's positive. So doing that, we plug in our 81. So x equals 81. 81 is positive, so we're good. So we know that that's our answer. Okay, and then for the next one, log base 4 of x plus 3 equals 2. So put this into exponential form. This is going to be 4 squared equals x plus 3. So this is going to be 16 equals x plus 3. Subtract 3 on both sides, we get x equals 13. So once again, we have to check. That's what's kind of annoying with these ones. We don't have a choice. It's part of the problem. So we have to make sure the input x plus 3 is positive. Okay, so x plus 3 is going to equal 13 plus 3. 13 plus 3 equals 16, which is positive, so we are good. Okay, let's make them a little bit harder. So 3 times ln of 2x equals 12. So first we need to isolate the logarithm. So that means we have to divide both sides by 3. So it's going to be the ln of 2x equals 12 divided by 3, which is 4. And now putting this into exponential form, this is the natural log, so it's base e. So it's going to be 2x equals e to the 4th, so that's exponential form. And solving this for x, we're going to divide both sides by 2. We're going to get x equals e to the 4th divided by 2. I'm going to leave it like that. You can plug it in your calculator if you want it as a decimal representation. But I'm just going to leave it like that. So let's make sure, we have to make sure the 2x is positive here. 2x is our input. Actually, I will use it as a decimal representation just because I've been doing that. So I'll have this x is approximately, what did I get, 27.3. So that's e to the 4th divided by 2. It's about 27.3. So we need to make sure that 2x, which is 2 times 27.3, is positive. That's going to give us 54.6. 54.6 is obviously positive, so we're good. So our answer, depending on how you want to write it, it's e to the 4th divided by 2, or 27.3 approximately. Okay, next one, we have log base 2 of x plus 20 equals 3. So the logarithm's already isolated, so converting this to exponential form, it's going to be 2 to the 3rd equals x plus 20. So I know sometimes I might write it a little bit differently when I'm doing exponential form. Like sometimes I'll write it, it's like x plus 20 equals 2 to the 3rd. Obviously it means the same thing. So this is going to be 8 equals x plus 20. Subtract 20 on both sides, and we get x equals negative 12. So we have to check this. So don't make the mistake in thinking that we got a negative, so automatically we have to omit it. We have to make sure this input is positive, not our answer. So we have to make sure x plus 20 is positive. That's going to be negative 12 plus 20, which is positive 8, which is positive, obviously. So that checks out and that works. So that's going to be one of our answers. Okay, let's do like 3 more. 6 plus 2 ln x equals 5. So we have to isolate the ln. We isolate the logarithm. Subtract 6 on both sides. So we get 2 ln x equals negative 1. And next we have to divide both sides by 2. So we get the ln of x equals negative 1/2. Converting this into exponential form, it's going to be x equals e to the negative 1/2. So natural log base e. So this is going to be, so you can 100% write it like this, or you can write it like x equals 1 over e to the 1/2. I'm actually going to write it over here. 1 over e to the 1/2. Or you can write it as 1 over the square root of e. So none of those are better than the other ones, but just so we know, they all mean the same exact thing. So I'm going to plug this in the calculator, and we get about 0.61, 0.61. So hopefully we knew that was positive, because 1 over the square root of a positive number is always going to be positive. So now we have to make sure that the input here, which is the x, is positive. So check, we have to make sure x is positive. So that just happens to be our answer here. Our x is 0.61, which is obviously positive, so we're good. So we didn't have to omit any answers yet, but it is coming. So let's do 2 more of these, and then we'll get into the last thing. So it's log base 2 of x plus log base 2 of x minus 7 equals 3. So a little bit of an issue here. We have 2 logs, and we can't isolate them. So we have to actually condense them. We have to condense using the, in this case, it's the product rule because they're being added. So condense using the product rule. So using the product rule here, it's going to be log base 2 of x times x minus 7 equals 3, which is the same thing as log base 2. I'm going to distribute the x squared minus 7x equals 3. So we have the exponent, or we have the logarithm isolated. So let's put this into exponential form. So base 2, so it's going to be x squared minus 7x equals 2 to the 3rd. And now this just turned into a quadratic, right? So it's x squared minus 7x equals 8. Quadratic, let's get everything on the same side. So subtract 8 on both sides and get x squared minus 7x equals, or x squared minus 7x minus 8 equals 0. So we hope that this can factor, and it can. So we factor it as x minus 8 times x plus 1. We set these equal to 0 separately. X minus 8 equals 0 gives us x equals 8. X plus 1 equals 0 gives us x equals negative 1. And now we have to check these. So we go back up, and we have to make sure we go back up to the original one. So we have to make sure x is positive and x minus 7 is positive. So check. I'll check it for, we'll have both of them. We'll start with x equals positive 8 it was. X equals 8. So we have to make sure x is positive. That's the first one here. So for this one, it's going to be, it's just 8. So obviously 8 is positive, so we're good. And then we also have to make sure the x minus 7 is positive. So x minus 7, that's 8 minus 7, which is 1, which is positive, so we're good for that one. And now let's check the x equals negative 1. So we need to make sure that x is positive and x minus 7 is positive. But our x here is negative 1. Negative 1 is not positive. Negative 1 is negative, obviously. So I'm just going to put a slash through it because it's not positive. So we have to omit x equals negative 1. So it's actually not a solution. So our only answer here is x equals positive 8. Let's circle it down here. So the reason why this happens when we do these types of problems where we get an answer but it's actually not an actual answer is because we changed the domain. The original domain for this question was everything greater than 0. And when we change to an exponential function, or we change it in exponential form, it changed to a quadratic. The domain for a quadratic is all real numbers. So we changed the domain, so we had to check our answers. Okay, so let's do one more similar to that, and then we'll get on to the last thing. So only a couple more pages left, I think. So log base 5 of x plus log base 5 of 4x minus 1 equals 1. So we have to condense these using the product rule again. So it's going to be log base 5 of x times 4x minus 1. And that's going to equal 1. So I'm just going to distribute the x and make it 4x squared minus x. And let's put this into exponential form. So it's going to be 4x squared minus x equals 5 to the first power, which is 4x squared minus x equals 5. I'm going to subtract 5 on both sides because it's a quadratic. We want it equal to 0. And that does not factor very nicely. Even if it does factor, it's not very nice. So let's use the quadratic formula. So the quadratic formula here is going to be x equals negative b plus or minus square root b squared minus 4ac, all divided by 2 times a. So let's plug in some of these numbers. Our a here is 4, our b is negative 1, and our c is negative 5. So it's going to be negative negative 1, which is positive 1, plus or minus the square root of b squared. B squared is going to give us positive 1 because it's negative 1 squared, minus 4 times a, which is 4, times c, which is negative 5, all over 2 times a, which is 4. Okay, so now we have to simplify. It's going to be x equals 1 plus or minus, in that, in the radicand here, it's going to be 1 minus 16 times 5, 16 times negative 5 rather. It ends up being positive 81 in there. So always just make sure you're careful with the negatives. We're subtracting a negative, so it's positive. So it's 1 plus or minus 81 over 8. This ends up being kind of nice because this ends up being 1 plus or minus 9 over 8. So that means we can split this up. X is either going to be 1 minus 9 over 8, or x is 1 plus 9 over 8. 1 minus 9 is negative 8. Negative 8 over 8 is negative 1. 1 plus 9 is 10. 10 over 8 simplifies to 5 over 4. So these are our two answers here, so let's check them. Going all the way back to the top. So check. For x equals negative 1, we have to make sure x is positive and 4x minus 1 is positive. So make sure that x is positive, but x is negative 1. Negative 1 is not positive, so we have to omit x equals negative 1 again. Okay, next we're going to check 5/4. So checking 5/4 here, plugging those in, we have to make sure x is positive. So x is positive because x is just 5/4. 5/4 is obviously a positive number, so that one's good. And next we have to make sure that 4x minus 1 is positive. So we have to make sure 4x minus 1 is positive. So plug in a 5/4 minus 1. That ends up being, the 4's cancel, we get 5 minus 1. That equals 4, which is positive, so that one's good. So we have to omit the negative 1, and x equals 5/4 is our only answer. Okay, so that's the first way that we can solve logarithmic equations. For this next way, next one is solving logarithmic equations using the one-to-one property. So the one-to-one property, if you remember when I was going over the inverses in inverse properties in section, I don't know, 4.1 or whatever it was. Essentially, if it's one-to-one function, it has an inverse. One-to-one meaning it passes the horizontal line test. So don't worry too much about the property name. This is the same concept as when we had common bases for exponential equations, where we just equated the exponents. This time we're going to get the equation in the form log base b of m equals log base b of n. So we get both sides to have the same log base b. Then we're going to drop the log base b's and equate their inputs. And then we're going to solve for the variable. And then we have to check the solutions in the original. And once again, we have to omit values that make the inputs negative or 0. Okay, so let's do, I think I have 2 examples of this, and then I have one little application problem that's relatively simple but pretty cool. So we have ln of x plus 2 minus ln of 4x plus 3 equals ln of 1 over x. So we need to get both sides to have just one little ln on each side. So that means on the left-hand side, we need to condense this using the quotient rule. So to condense this using the quotient rule, it's going to be ln of x plus 2 divided by 4x plus 3. And we know we needed the quotient rule because it was being subtracted, right? So it's going to be equal to ln of 1 over x. So now we have the same log on both sides with nothing else, nothing being multiplied on it. So what we can do is drop the log, and then we're left with x plus 2 over 4x plus 3 equals 1 over x. So technically what we're kind of doing there is like base e both sides, because that cancels the ln's on both sides. So now we have this it's a rational equation. So we're going to solve this by cross multiplying. So cross multiplying, we get x times x plus 2 equals 4x plus 3 times 1, so just 4x plus 3. And we're going to distribute the x and get x squared plus 2x equals 4x plus 3. So we have another quadratic. Let's get everything on one side and set it equal to 0. So I'm going to subtract 4x and get x squared minus 2x, subtract 3, x squared minus 2x minus 3. And then we hope it can factor, and it indeed can factor. We get x minus 3 times x plus 1, 2 numbers that multiplied to negative 3 that added to negative 2. So that's going to give us either x minus 3 equals 0 or x plus 1 equals 0, which is x equals 3 or x equals negative 1. Okay, so hopefully that's not too bad, but we have to check it, unfortunately. So checking it, let's check x equals, what did we get down here? X equals 3. We're going to use that. We have to make sure x plus 2 is positive, 4x plus 3 is positive, and 1 over x is positive. So I'm going to skip making you guys look at all this because you can probably see that all of these are going to be positive, so I'll pause it and just write it. Okay, so I just plugged in the 3 into all of those x's and all of those inputs, and I show that all of those are going to be positive. So now let's go in and plug in x equals negative 1. So when we plug in x equals negative 1, we're going to make sure that the first one was positive. So we make sure x plus 2 is positive, which it is. It's negative 1 plus 2, which is 1, which is positive. So that one's good. For the next one, we're going to make sure that 4x plus 3 is positive, but that's going to be 4 times negative 1 plus 3, which is negative 4 plus 3, which is negative 1. That is not positive, so we have to omit x equals negative 1. So that's not a solution. So we cross it off, and we get x equals 3 as our only solution. Okay, so let's do one more of these ones. So we have ln x minus 4 plus ln x plus 1 equals ln x minus 8. So we need to use the product rule on the left-hand side to combine them. So it's going to be the ln of x minus 4 times x plus 1. We knew it was product rule because they were being added. And I'm going to just multiply x minus 4 times x plus 1. So that's just distributing, where you have to FOIL that, we end up getting x squared minus 3x minus 4 equals the ln of x minus 8. So once we get these ln's on both sides like that, once again, we can drop them and equate what is on the inside. So x squared minus 3x minus 4 equals the ln of, or equals x minus 8. ln is gone. X minus 8. So quadratic, hopefully you're getting the hang of this and you keep on seeing quadratics. They tend to pop up a lot. So subtract x and add 8 to the left-hand side. We're going to get x squared minus 4x plus 4 equals 0. And then you hope it can factor. If not, quadratic formula, but this can factor x minus 2 times x minus 2. I'm going to write this as x minus 2 squared. I just think it's a good habit to get into. And solving this for 0, we square root both sides. So we get x minus 2 equals still 0. Add 2, we get x equals 2. So let's check this. So we have to make sure x minus 4 is positive, x plus 1 is positive, and x minus 8 is positive. So make sure, what was it? X minus 4, we'll start with that one, is positive. So we plug in a 2 here, and we get 2 minus 4, which is negative 2, and that is not positive, so that was easy. We just have to omit x equals 2 right away. We don't even have to check the other ones. So this actually, we omit that. So there's actually no solutions here, which is okay. Okay, so there's no solutions for that one. Okay, so one more thing here, just to kind of have like a, not really a huge summary because we still have the next section to go, but just some important applications here that get used all the time. So something like compounding interest, obviously that gets used with exponentials all the time because we've already done it. Exponential growth and decay, which we'll actually be doing that in chapter 4.5, as well as radioactive decay. So that stuff is pretty interesting. Magnitude of an earthquake on the Richter scale, that's measured using logarithms, I believe. And relationship between the hydrogen ions concentration and the pH of a substance, which we'll see in this last example. And frequency ratios, like musical tones and intervals, are also used using logarithms. Okay, so obviously there's more than just that, but those were a couple of interesting ones that I thought that were pretty different from each other. So let's do, I believe this is the last thing, one more example here, just for one extra little application that's pretty simple. So the pH scale, like I had mentioned above, pH scale and the concentration of hydrogen ions are related using logs. So the pH scale for acidity is defined by the pH equals negative log of the concentration of hydrogen ions. So that H plus is the concentration of hydrogen ions, and it's measured in moles per liter. And if I remember correctly, I'm pretty confident, the M that it stands for is the molarity. So that's why it's just capital M for moles per liter. Okay, so let's do two questions using that little equation. So a sample of milk has a hydrogen concentration of approximately 0.0000125 molarity. What is the pH? So we're looking for the pH of milk given the hydrogen concentration. So using this formula here, we're looking for the pH. So pH equals negative log of the concentration of hydrogen ions. So we have the concentration of hydrogen ions. It's about 0.0000125. So I'm going to plug that in. So it's going to be pH equals negative log of 0.0000125. I'm going to leave out the units. So plugging this in the calculator, this is base 10, right? If base isn't written, it's base 10. So plugging this in the calculator, we end up getting a pH of approximately 4.9. So that seems a little bit too acidic for milk, but so that would be the pH of that milk sample. And then for the next one, the pH of vinegar is 3. So we want to know the hydrogen concentration. So this time so same formula, pH equals negative log of the hydrogen concentration. The pH is 3, so 3 equals negative log of that hydrogen concentration. So we need to, this is going to be, we're solving for the H, right? So it's like we're solving for X, so it's a logarithmic equation. So we need to isolate the log, meaning we need to negate both sides first. So divide or multiply both sides by a -1 to get that negative off the log. And now we need to base 10 both sides. So base 10 both sides to convert it into exponential form. So it's 10 to the -3 equals the hydrogen concentration. So the hydrogen concentration of vinegar is 0.001 moles per liter. Okay, so yep, that is it for section 4.4.